Let's continue our studies by focusing on the network time protocol implementation within Red Hat Enterprise Linux. We'll launch a shell and open our notes and begin discussion momentarily. Let's maximize gedit. And we'll label this section Network Time Protocol Implementation. The acronym for Network Time Protocol is NTP, and it features the ability to synchronize your system's clock, and it optionally features the ability to synchronize other clocks. Also can be used to sync other clocks, providing that those other clocks, regardless of device type, whether an infrastructure system such as a router or a firewall, or even an operating system such as Windows, FreeBSD, or Linux, or Solaris, so long as network time protocol support is built in or included by way of a daemon or service, and the version of network time protocol works with the version implemented by Linux, which is version 4 and older, such as version 3, 2, and even the older versions of the protocol, then the client contacting your server will be able to synchronize their local clock. So with that said, how is it implemented on the system? From the shell, again, it hasn't changed from the implementation with Red Hat Enterprise 4 or even 3 or Red Hat 9 for that matter. What has changed is the version of the package that's used to implement NTP. From the shell, an RPM query all grep NTP reveals the name of the package momentarily, and its version 4, major version, minor version .2. NTP came up in this path as well. An RPM query list of NTP enumerates its contents as expected. We'll scroll up towards the top, where you'll see it maintains an etc NTP directory, and ntp.conf. This is the main configuration file. So let's just note this implemented as NTP 4.2.rpm package, and the etc ntp.conf is the primary configuration file. So when you've determined that you want to synchronize your clock against other systems or turn on, let's say, the signature feature, you'll do so through the etc ntp.conf file. Another feature is that NTP works based on a hierarchy, so is hierarchical, using stratum, or strata that is, various stratum levels, but using strata levels to dictate or to influence or to denote accuracy, and that is clock or time source accuracy, which we need to talk about before we get into the main configuration file. So let's label this section or subsection NTP strata, and what you basically have is the ability, let's just bring this back in, the ability to denote clock accuracy based on stratum, with stratum level 1 being the most accurate, as an NTP server at this level is connected to an external time source. And the protocol provides the utilities necessary to determine the various strata. And an external time service includes, but not limited to, GPS, radio, etc. So NTP has this built-in hierarchy called NTP strata, And each clock in the NTP strata registers its stratum level depending on what source it is using to obtain its time information. So if our clock uses a stratum 2 level clock, then our clock or our server becomes a stratum 3 time server, so on and so forth. If we are at stratum 5, or if we authenticate against a stratum 5 clock, then our clock will become a stratum 6 clock. If we authenticate against a stratum 1 clock, our clock becomes a stratum 2 clock. So the hierarchy is very easy to understand, and you should aim to synchronize your clock against low-level stratums such as 1 or 2 to ensure accuracy. But the variation across strata is so small it's measured in milliseconds, which means your accuracy will be high, relatively speaking, anyway. So if you decide to authenticate or get your time source synchronized against a time source that's at stratum 2 or 3, you won't be terribly off from stratum 1 or even 2, depending on the level that you authenticate or synchronize your time source at. Now, regarding those various strata levels that you may synchronize your clock against, you can find resources, public NTP resources, by navigating to www.ntp.org. So use ntp.org to locate public NTP clocks at various strata. But before doing so, we should also note that by default, NTP is not enabled, and we need to enable it. Let's just take a look at the shell to determine whether or not it's enabled. We'll let you in as a root user, and once in, we'll execute a service NTP. And again, it's the way it's listed, just so you don't have to memorize it. In etc initd, NTP is listed as NTPD, so there'll be a service NTPD status. This will tell us whether or not it's running. Also, since we now know how to use checkconfig list NTPD reveals that it's turned off in all run levels. So our clock, our local clock, currently does not synchronize against an NTP server, which means when you execute date, the time that's returned, the date and time that's returned, is based on the time that's set in the BIOS and the time that you set up during installation of Red Hat Enterprise Linux, which may or may not be tied to the BIOS, but it's derived initially at least from the BIOS. Whether or not the OS controls the BIOS is a separate question. But nonetheless, this time source is local and not remote. And again, to ensure that your operating system is time-wise synchronized or as close as possible to what is known and accepted as standard time, as governed by the Network Time Protocol, you need to configure your NTP instance, the NTPD instance, to synchronize against remote time services. Now again, the time service doesn't have to be an internet time service. We've got in our environment a time server. Let's just navigate to our graphic and identify that server, which we can use. This is the classroom topology. For the time being, we can choose to synchronize against our Linux CBT Media 1 box. That's this box here, the 75100 box, as it's running NTP. Just to illustrate how NTPD works. To do so, we need to include, so our first task is to sync against internal NTP server. And to do so, we'll modify etc ntp.conf with the following entry. Server followed by the IP address or name, hostname if hostname is resolvable, of the NTP server. Its IP address is 168.75.100, but if, again, DNS is in order, or if the etc hosts file has an entry, it would suit us to use the name. In the event that the IP address changes, it would then render us with one less change. We would not have to update the NTP configuration file. So let's go ahead and paste this directive in the primary NTP configuration file located in etc ntp.conf. Notice that there are some server lines defined to connect to Red Hat Enterprise Linux servers at pool.ntp.org. That's for this local system. How about for our remote system? Let's see what's configured. We'll open another shell and SSH is root to 75.199, which is running the 5.1 release, and see what it's configured to do, and then make the determination as to which one to modify. This server doesn't appear to have any server lines enabled. In fact, it has an internal server line enabled, this remote system. So here's an example of a remote system which authenticates, or synchronizes that is, against an internal network time protocol server. We can include a comment, internal NTP server. And there's an entry for the loopback adapter in the event that NTPD is started with no reference to an external or other time source that's more accurate than the local system. NTPD will work against the local clock, and it will use it as a time source if nothing else is indicated. Now on the remote system, let's execute service NTPD status to see whether or not it's running, and as you can see, it's stopped. Also, check config NTPD shows that it's stopped. So with that said, let's start the NTPD service. To do so, simply execute. So step B is to execute service NTPD start, and this starts the NTPD service. And then we'll also execute for subsequent reboots of the system, check config NTPD on, which will turn it on. Let's go ahead and copy and paste this. And we'll do this on both systems to ensure that the clock is running on both. So this starts the daemon, and then let's execute check config NTPD on, and now it's going to be set to start in the appropriate multi-user run levels 2 through 5. So how do we go about confirming whether or not NTPD is up and running? Well, once it's up and running, we'll list as step D, use NTPQ NP. This queries the running NTPD server, and it returns status information including whether or not the local NTPD server has synchronized against a remote NTPD server, and whether or not it has contacted all of those NTPD servers, one or more of course. So there we've executed NTPQ-NP. NTPQ is the Network Time Protocol query utility. It returns a series of columns, including the IP address of the remote system, or if it's a clock that's connected to the local system. So if we're a Stratum 1 clock and we have a GPS or external time device, it'll list the type of device, which would in all likelihood require some form of a driver in order to talk to the local clock. And otherwise, NTPD returns in the remote column the IP address and optionally the host name of the remote NTPD server. So here we see 192.168.75.100 as well as our local loopback clock. And again, the local loopback clock is indicated in the etc ntp.conf file. It's a backup clock that's to be used, and it's auto-assigned stratum level 10. Again, the higher the stratum number, the less we can trust, or the less NTP trusts the time source. It's deemed to be not as accurate as a lower stratum number, such as 3. Now also notice that for the remote time server, Linux CVT Media 1, there's a column which is reference ID. This column tells us, the NTPD administrator, where the remote clock has gotten its time from. So this Media 1 box is currently at stratum level number 3 and is getting its information from a Stratum 2 clock. The stratum, a combination of the stratum and the reference ID columns, can tell you the stratum level that the remote server's NTPD sync clock is at. So when we use a server and we see the stratum level that the server is at, in addition to the reference ID, which is usually an IP address of another server, we can tell the stratum level of the other server, because NTP is hierarchical. So this tells us that the 207.210.74.166 clock is operating at stratum level number 2, rendering our internal server 192.168.75.100 at stratum level 3 clock. We are now synchronizing this Red Hat Enterprise box Linux CBT Serve 4 with an IP address of .199 against an internal server with an IP address of .100, which renders our clock, our local system, a stratum 4 clock. So let's just note NTP synchronization is hierarchical. Thus, if we sync against a stratum 3 clock, we become a stratum 4 clock, meaning if a host synchronizes against us, then we will appear to be a stratum 4 clock, which denotes the accuracy level with respect to how close the clock is to an actual external time source. There are other values that are kept, whether or not the item's up, whether or not it's reachable, when to contact it, when to poll it, delay, offset, and jitter columns, which again are metrics maintained by NTP to determine how accurate and how far and how much of a trouble it is to contact the clock. NTP also has a built-in algorithm to assign a clock as the default reference clock, indicated by the asterisk that you see next to the clock. So this asterisk juxtaposed to the IP address for our stratum 3 clock denotes to us that NTP has chosen this clock as its default clock. So if we had a list of 5 clocks, wherever you see the asterisk indicates the clock that your NTP server is currently using. And NTP will then set your local clock based on the default server's IP address and time information. And that brings up another point. Since NTP has the ability to change the local clock on your system, you want to be sure that you have vetted the remote time server. You want to be sure that it's a trusted source. You can find trusted sources from the ntp.org site. Just pull up a browser and navigate to that site. We'll just launch an instance here to show you. And from that site we'll find references to various universities and companies located all across the world that are known to be trusted time sources. And this will come up momentarily. And usually on the right-hand side of the page is a link to the various servers. And you can pick your server by region of either this country or any other country in the world to determine whether or not the clock's close to you. So if you live, let's say, in Rio de Janeiro, Brazil, you'll want to pick a clock that's close to Rio de Janeiro, Brazil. Now we'll wait for this site to load, and while it loads we'll continue our discussion. It will come up momentarily in the interest of saving time. So we're syncing against a stratum 3 clock. We have become, as a consequence, a stratum 4 clock. How can we prove that we've become a stratum 4 clock? Well, that brings us to our next task. Prove that Linux CBT Serve 4 is indeed a stratum 4 clock. To do so, we'll modify the etcntp.conf file of the local system, Linux CBT Serve 1. And we'll modify it to synchronize against the stratum 4 clock. So A1 will be to insert server 192.168.75.199 as a time reference, as an NTP time reference, and then start our service locally. So let's find a local instance. We'll modify etcntp.conf. We'll comment the references to the Red Hat Enterprise clocks and just insert our own instance of a clock. And we'll insert also a comment testing local sync. And then save the changes. Now again, we need to start the service. So let's find service in our history. start it, and we'll also check config NTPD on to ensure that it's in the appropriate run levels when we reboot the system. And again, let's just ensure that check config returns what we expect, because if you are pursuing examination, you need to ensure that the service will restart in the appropriate run levels when you have, or will start when you have changed run levels, let's say from 5, which is the current, to 3, or you may navigate to single user mode, then return to multi-user mode. In any event, or in either case, the NTPD service should start. Now let's query locally to confirm that we are synchronizing against a Stratum 4 clock using NTPQ NP. And it will take a little while to return it, but nonetheless we see that 199 is in our list of clocks to consult. However, stratum information is currently set at 16, which is the last stratum, which means the clock is unreliable or should not be trusted. Now this also could be because of security concerns between our local system and the remote system, meaning IP tables configuration, firewall configuration. And we'll try it again. And now it appears to be attempting. Often you'll find stratum 16 until the NTP server is able to determine the stratum level of the remote server. So eventually we'll see that this comes back at stratum 4, but this won't prevent the clock from synchronizing. For example, currently it sees that local is set to a lower stratum level, so it will use the local clock until this remote clock obtains a lower stratum level, or in other words, until the local NTPD server is able to determine the status of this remote clock. So eventually that will resolve itself, but again, you can use remote clocks from the NTP.org website, navigating to the time servers link and just finding time servers that are in your vicinity, such as from a university or a big company that's been gracious enough to publish NTP servers. And the suggestion is that you supply your NTP server with at least 3 clocks so that it can determine which clock is the most accurate, and also for redundancy. So note, ideally you should supply, which explains why we saw 3 entries for Red Hat Enterprise Linux clocks in the default configuration. So you should supply your etcntp.conf file with at least 3 clocks for the following non-inclusive list of reasons: to determine accuracy, which is built into the network time protocol, as well as redundancy. In the event that one clock goes offline, at some point the network time protocol daemon will determine that it's offline and attempt to contact another clock. And the NTP daemon is always checking to see whether or not a clock's available and if it's still accurate by maintaining a list of offset, delay, and jitter direct values, metrics, and calculates based on those metrics. So with that said, we should place other clocks in. Now, in the case of the Red Hat Enterprise Linux clocks, let's nano etcntp.conf. They'll definitely respond. These pool clocks, if we uncomment them in addition to the 199 hosts, and we could even add, we have a clock internally at 100, the Media 1 box, and then restart the NTPD daemon using service NTPD restart or etc initd. Here's an optional way, etc initd NTPD restart. Now when we re-execute NTPQ NP, you'll see all of the clocks. Notice the internal clocks haven't resolved as we expected. However, the external clocks have. And we see that of the 3 Red Hat Enterprise Linux clocks with the pool addresses, 2 of them are at stratum 2, whereas the third's at stratum 3. The 2 that are at stratum 2 reference stratum 1 clock. So this 216 and this 217 clock reference these distinct IPs, 132 and 18 respectively, at stratum 1. These clocks in turn reference official time sources. So we could, if we wanted to, directly reference the stratum 1 level clock by updating our configuration. Let's nano it, and we'll just place it somewhere on the list. Doesn't have to be in any specific order. NTP will make the determination as to the accuracy by simply contacting the clock. Let's restart NTPD, clear screen, and then rerun NTPQ, the query utility, to determine what's going on. Now currently we see that the 132 clock was contacted. It took a while. Also notice it took a little while, but the 100 clock was contacted at stratum 3. So it takes a while for resolution to happen. By a while we mean sometimes 10 seconds up to a minute or a couple minutes, depending on network latency. So we do have a stratum 1 resource. And in all likelihood, the stratum 1 clock will become our default clock because it's more accurate than any of the other clocks. Also notice that with the stratum 1 clock, it references a GPS source for time, which is accurate. So this clock, in all likelihood, will become our default clock. But again, for each clock, metrics such as when it was contacted, the pulse interval, if it was reachable, the stratum that it's at, whether or not it's up, the delay, offset, and jitter are maintained for each and every clock that we communicate with, and NTP crunches the numbers to determine who's accurate. It still has not determined which clock will become its master or trusted clock, but it will at some point. So indicate as many clocks as you'd like. Ideally, specify at least 3 clocks. And depending on the clock that becomes our default clock will determine the stratum level at which our local system operates. So if the stratum 1 clock becomes our default clock, we become a stratum 2 clock for which internal resources can be used to synchronize against. For example, a Cisco router could use or could synchronize against our internal clock. That would certainly not be a problem. In fact, let's SSH into the router. And once there, we'll just navigate into the config mode and execute the NTP server command, followed by the IP address of our local system, which is .10, the Red Hat system, Enterprise 5. This will attempt to synchronize the router, and now when we execute show NTP associations, we'll see at some point that it has contacted and assigned a stratum level to our clock. Notice the router is using currently the Media 1 box 75.100 at stratum 3. But over time, when it is able to communicate with our internal system, the new system, let's update the configuration, it will determine that it's a stratum 2 level clock and use it over the stratum 3 level clock, Media 1. So it'll take a little while, but it'll update, and throughout our studies of other items, we'll check in just to see where it's located. But again, just to recap briefly the way NTP works. First and foremost, it works without much intervention. There isn't much for you to do other than to define servers that are to be consulted, NTP servers, in the etc ntp.conf file. You also need to, of course, start the service and ensure that NTPD starts in the desired run levels. But the key thing is to assign a server or more in etc ntp.conf, and you may optionally apply security to the configuration file, but then you need to ensure that the other NTP peers and servers with whom you communicate are configured with the appropriate security directives to be able to communicate. So if you turn on security on one after consulting the documentation, be sure to turn on or enable security on the others, since NTP servers will naturally function as pairs if they're referenced via the etc ntp.conf file. The protocol works in a hierarchical nature, with stratum 1 clocks being the most accurate clocks because they're connected to external time sources such as GPS. And it goes all the way to stratum 16, which is considered inaccurate and should not be used. So whenever you start NTP, initially all clocks are set to stratum 16 with the exception of the localhost clock, which is assigned stratum 10. Stratum 16 means the clock is not to be trusted. However, 15 through 1 should be trusted. And the differences between the strata levels are minor and are measured in milliseconds and not in full seconds. So even if you synchronize at a stratum with a stratum 12 clock, you're likely to be just slightly off from synchronizing with a stratum 2 or 1 clock. So go ahead and find a clock to synchronize with at ntp.org. The site's coming back pretty slowly, but we'll look at it later on to see where you can pick out lists of clocks. A standard hierarchy in a corporate environment is to set up one or more, preferably 3 internal trusted time resources. So you pick, let's say, 2 Linux boxes and maybe a Cisco router, and set them up as your trusted internal network time protocol servers. Then have those 3 systems, let's say these 2 Linux boxes and the router, consult external time sources. So in fact, your router and the 2 Linux systems will become Stratum 2 clocks. You then have all of your other systems, such as Windows, Red Hat, Debian, so on and so forth, synchronize against those trusted internal time resources, and they'll be at Stratum 3. But ideally, have your internal hosts synchronize against your internal Stratum 2 or 3 clocks, which reference outside sources. And of course, if you have an external time source such as GPS configured, then by all means use it, and you'll become a Stratum 1 server. So it's hierarchical. It works by default. NTPQ handles the display of information. We've been using NTPQ with the NP option to not display names, but, and notice at this point, the asterisk is assigned to the GPS clock, the Stratum 1 clock, indicating this is our trusted clock. And there are candidates included with the plus symbol, candidate clocks, other clocks that are to be trusted, including the Red Hat Enterprise Stratum 2 and our internal Stratum 3 clock. Whereas it doesn't trust the 199 clock, which again could be some sort of IP tables which we haven't looked into. We'll look at it in the security section, reason why it's not communicating. But it has assigned a Stratum 11 to it. You drop the N option and it will perform name resolution. So here's the name resolution. We're currently trusting bigben.ucsd.edu. This is our clock. But name resolution returns when you drop the N option, just like using netstat. This NTPQ utility is both interactive and non-interactive. Run it with no options and it propels you into interactive mode, at which point you can type help to see the different commands that you may execute, such as associations. And this returns the different associations, reachability, so on. Peers. These are other clocks that you've paired up with. And many other items. You can print a current time, see the version of NTP that's currently being used by the NTP daemon. Again, it supports multiple, but it's claiming to be version 2 for compatibility reasons, and you can force that through the configuration, and so on. Again, NTPQ is the main utility. Now, there are other utilities in addition to NTPQ, such as NTP date, which can be used to immediately set your clock to the time of a remote clock. For security, there's NTP key generation, which allows you to generate a key, a synchronous or synchronized shared key, to be used between 2 NTP servers for security, to prevent other clocks from influencing your local system's clock. There's also NTP trace. This allows us to trace the path between our clock and our trusted clock. So it shows localhost, that's our clock, which is assigned Stratum 11, and the Stratum 1 clock that we ultimately trust. So it traces the path between the NTP path between our clock and the trusted clock. And again, other utilities like NTP time, NTP DC, but the key ones include NTPQ as well as NTP date and trace, and optionally NTP keygen for generating shared keys between servers. So the protocol is up and running. Just be sure that you start it, you set up the configuration, then start it, and ensure that check config enables the clock. And if you see that you're unable to synchronize with an internal clock, chances are IP tables or an ntp.conf directive is blocking it. You can just man NTP to find out more information about a directive that could be blocking. It's usually a restrict directive. So with that said, we've looked at NTP, and we're going to move on to other daemons.